Welcome back one last time to Physics 371, where I will now show you one of the last things that we have to do to our equations of electricity and magnetism in order to arrive at the modern version of what are known as Maxwell's equations. So remember that we've been talking about how Faraday's work showed how to generalize the equation for the curl of E to the case of electrodynamics. For electrostatics, we know the curl of E is equal to 0, and so Faraday showed that you can have electric fields that circulate and therefore have a curl if you've got a changing magnetic field. So when Maxwell began his work in the mid-1800s, here was the state of the art. We had Gauss's law. Del dot E is rho over epsilon 0. Del cross E is minus dB dt. Del dot B is 0, and del cross B is mu naught J. So that might seem like it's okay and we're fine, but as we'll see in just a moment, inside these equations lies a terrible inconsistency. And it has to do with the fact that in order to be mathematically consistent, the divergence of the curl of a vector function must be 0. So let's check that out using these equations. Let's take the divergence of the curl of E and then the divergence of the curl of B. So first, the divergence of the curl of E, that's pretty easy to do. So that's del dot negative dB dt, which we can rewrite as minus the time derivative of del dot B. And of course, del dot B is equal to 0. And so this time derivative is always 0, and that checks out. That's great. Now, what about the divergence of the curl of B? So putting in the mu naught, that will be the mu naught times the divergence of J, and we see that this causes a problem. Now for steady currents, as I'll show you in just a minute, this term on the right-hand side is always 0. So in the realm of magnetostatics, we're fine. But it's not true in general. And so this produces a real problem for the theory of electromagnetism, which Maxwell, to his great credit, realized mathematically. So there's a nice geometrical way to see how this inconsistency arises, and to give it a little bit of physical meaning, let's imagine that we have a charging capacitor, so that when we close the switch, there's a power supply. These two plates of a parallel plate capacitor, I've drawn them pretty far apart so that I can do another illustration in just a moment, but this is an example where once we close the switch, there will be an initial current flow, but then as the charge builds up on the capacitor plates, the current will eventually fall to 0. So while the capacitor is charging up, the current is falling from an initial value I0 down to 0. And we'll see that this, in this physical situation, is a real inconsistency in the application of Ampere's law. So integral around a closed loop of B dot dl should be mu naught times I enclosed, but here's the problem. I enclosed depends on which surface you use. For example, if I make a surface that's composed of a circle, a planar circle that cuts through the wire on the outside of the capacitor, we'll call that surface 1. That's it's the loop 1, but if the surface that we use for determining the enclosed current is the surface that's just the plane of that circle, then it's easy to see that I enclosed is just whatever the current in the wire is. However, let's imagine that consistent with that loop, we determine I enclosed by looking at a different surface, and this one is a little bit like kind of a sideways fishbowl or candy jar, where this surface 2 is still bounded by the circular loop, but it has its surface in between the capacitor plates where clearly there's no current flowing. So if I were going to determine I enclosed through that surface, I would get 0. So somehow there's a problem, because if I pick this circular loop to evaluate B dot dl, I ought to get the same thing on the right-hand side, no matter which surface I use that's bounded by that circular loop. And yet, clearly, two different surfaces here would give me two different results on the right-hand side. Ampere's law is inconsistent, and that makes no sense. So what did Maxwell do? Well, he realized that in order to make Ampere's law consistent, there must be some kind of, I'll put it in parentheses in the quotations, current. There must be some kind of physical quantity that acts like a current that's flowing between the capacitor plates. And we can see how this arises by evaluating the divergence of J. All right, going back to what I did just a minute ago, I said that the divergence of the curl of B should be 0. So using Ampere's law, you get mu naught del dot J, and there was an equation that showed us how to simplify del dot J back in Chapter 5, and it was called the continuity condition. So del dot J was minus the time rate of change of rho. And remember, this came from assuming that there's a region of space where there's some current flowing, and the amount that flows out through a particular surface has to be equal to minus the time rate of change of the charge inside that surface. So this is really just a physical condition that arises from the conservation of charge. That's why it's called the continuity condition. But we can also use Gauss's law, and remember, del dot E is rho over epsilon 0. So if I just solve for rho from Gauss's law and substitute in here, then the divergence of the curl of B is equal to this term on the right-hand side. Right? So we're now just taking what we started with and what we end up with on the right-hand side and pulling the divergence outside and putting everything else in. The only time-dependent quantity that we have is potentially the electric field. So what we're seeing is that assuming that Ampere's law had the form that we started with originally, we get a non-zero value for the divergence of the curl of B, and that non-zero value arises from a changing electric field. All right, so now we're beginning to see what's causing this magnetic field. It's a changing electric field in between the plates of the capacitor. So what did Maxwell do? Here's what he did. He said that in order to fix this up, I have to do something to Ampere's law that will make the divergence of the curl to be 0. Well, since the divergence of the curl of B with Ampere's law in its original form is this, with a negative sign in front of it, why don't I just add this term in the parentheses to the right-hand side of Ampere's law? So if I do that, what it will achieve is it will guarantee that when I take the divergence of the curl of B, I'll get 0. Because remember, the divergence of mu naught J gives me this term up here with a minus sign in front of it. So that then, adding this term to the right, if I take the divergence of both sides, I will get 0. So totally mathematically, in an abstract way, Maxwell fixes up Ampere's law by adding this extra term. And again, before we go any further, just take a look at this equation. We know that a circulating B field can be produced by a current. Right? That was what Ampere's law told us in the first place. But now we see that in order to be physically consistent, mathematically consistent, there must be a way of generating a circulating B field through a changing electric field. And that is what this second term on the right-hand side means. We sometimes call it the Ampere-Maxwell law to recognize the important role that Maxwell played in putting it in this final form. So it guarantees that the divergence of the curl of B is 0, and this repair is identical to adding another component to the current density in the original Ampere's law. So if I take the original Ampere's law and just say, well, J must be composed of the net J must be composed of the J due to any currents plus a term that depends on the changing electric field, then we recover the right expression. So J net is J plus this term epsilon naught times the time rate of change of the electric field. And Maxwell called this second term, he called it the displacement current. Now it's not really a current because it's not a flow of charge. However, it has the same dimensions as a current, and the reason he called this the displacement current is that in a vacuum, right, we know there's a relationship between D and E and the polarization P. So in a vacuum, the polarization P is 0, and epsilon naught E is simply D, the electric displacement. So we call it the displacement current because in a vacuum we can write this as J sub D is dD dt. And I guess he looked at this and said it's a time rate of change of D, so it's some kind of current, not physically a flow of charge, but a changing electric field. So just as a changing magnetic field induces an electric field, that's what Faraday found out, now we see in this new version of the Ampere-Maxwell law that a changing electric field induces a magnetic field. And this is a kind of aesthetically pleasing symmetry. So it gives us Maxwell's equations in their final form, a complete set of equations. And it shows us on the left-hand side that we can generate electric fields from charges, and those are electrostatic fields that have a non-zero divergence, or we can generate electric fields that circulate by having changing magnetic fields. On the right-hand side, we see that there's no such thing as a point source of magnetic fields, but we can generate magnetic fields in two separate ways, through a steady current, J, a flow of charge, or through a time rate of change of electric field. So they even look more symmetrical, these equations for E and B, if we apply them to a region of space where there are no charges and no currents. So that means that that Gauss's law becomes del dot E is 0 because there's no charge. Del dot B we know is 0. And Faraday's law is the curl of E is negative dB dt. And if there's a region of space with no current, then the curl of B is mu naught epsilon naught times dE dt. So these equations, apart from the constants that are in the expression for the Ampere-Maxwell law, the only remaining asymmetry is this minus sign that we see in Faraday's law. So Maxwell's equations, along with the Lorentz force law that tells us how a charge experiences a force from an electric or a magnetic field, those equations form the fundamental basis for all of electromagnetism. And I'll see you in class. We'll explore some of the implications of these things, and then we'll finish the semester by showing how these equations and just some very simple mathematical manipulations give us the physical basis for electromagnetic waves.